Okay, welcome back. In this chapter, we're going to talk about continuous probability distributions. In particular, we're really interested in the normal probability distribution. Okay. Now, in the previous chapters, we talked about discrete random variables, right? This time, we're going to be talking about continuous random variables. Okay. All right. Now, the main distinction here is that discrete random variables are countable values. Okay, continuous random variables are not countable. There's actually an infinite amount of outcomes. Okay, so what we were able to do in the discrete probability case was we were able to create tables. So for discrete random variables, we were able to create tables, right? And we know that the sum of all the probabilities, right, of every value, like 0, 1, 2, dot, dot, dot. The sum of all these probabilities would always add up to be 1, right? Well, now for continuous random variables, we actually don't have this luxury. Okay, we can't create a table like this. So if we don't have a table, then what can we use? Well, for discrete random variables, we were also able to create histograms, right? We were able to create histograms for each one of these probabilities, right? Something like that, right? We're going to be able to do something very similar for continuous random variables. Okay. And the continuous random variables that we're going to be talking about is, like I mentioned, the normal distribution. But we're going to start off with the uniform distribution. Okay. There are some applications for the uniform distribution, which we'll talk about in a little bit. But mostly the reason that we're talking about the uniform distribution here is because it's very easy to show you how we calculate probabilities with the uniform distribution. And we're going to use those stepping stones, really, they're just like baby steps, in order to talk about the normal distribution. Okay, so as I mentioned earlier, we have an infinite amount of possibilities when we're dealing with continuous random variables, right? So, for example, the probability of some random variable equaling any particular value out of infinity, well, any one value out of infinity is technically 0. Okay, if you put a really, really large number in your calculator, do like 1 divided by 999999999, you'll get something very close to 0. Okay, so that, again, we can't use probability distribution tables to express this because you'll just have a bunch of zeros here. But we're going to do something a little bit different for continuous random variables. So what we're going to use is a probability density function. This is an equation or a graph that's used to specify and compute probabilities of a continuous random variable that must satisfy 2 properties. And those being, well, if we create a graph, then the total area underneath the graph is always going to be equal to 1. So that's kind of similar to when we're dealing with probability distribution tables where the sum of all the probabilities is equal to 1. So that's analogous to that. So the total probability is equal to 1, yeah. And the probabilities are always greater than or equal to 0 or less than or equal to 1. Okay. Now one question remains is that how do we use these density functions to find probabilities of the continuous random variables? Well, if we can calculate the area underneath the curve, which we did say that it was equal to 1, then that's how we're going to calculate probabilities. Okay, let me show you how that's done. So to illustrate areas and their connection with probability, we're going to start with the uniform density function. This is the most simplistic continuous random variable to start talking about areas and probability with. So a uniform density function is essentially, it's a random variable where the values are anywhere between your value A and your value B, and there's a uniform chance of that occurring between that interval. And everywhere else it's 0. Now, in order for this to be a probability distribution function, this area here has to be equal to 1. So what we have here is a rectangle, and the area of a rectangle is equal to base times height. Okay, so we have a base times a height, right? this would be our base, and this would be our height. Well, if we're doing math with these symbols here, the base right here, well, this length would be b minus a, right? Now, what would the height have to be? Well, it tells us right here that it's 1 over b minus a. And where is that coming from? Well, we have to force this height to be a number such that when you multiply it by b minus a, it does give you 1. Okay? So the only way that can happen is that the height must be 1 over b minus a. So therefore, it cancels out and gives us 1. Okay. Now, that looks a little abstract if you're not really comfortable with all those letters. Let's actually do an example to illustrate what I'm talking about here. Example 1, you arrive at a train station and all you know is that the train will arrive sometime between now and 50 minutes from now. Okay. The chance that the train arrives during the first 5 minutes is the same as for the last 5 minutes. Therefore, the amount of time that you wait for the train follows a uniform distribution. Okay, so essentially there is an equal amount of chance that the train will arrive anytime between now and 50 minutes from now because it's on a schedule. All right, so let's let x be the amount of time that we wait until the train arrives. Okay, so we're defining our random variable x as the time it takes for the train to arrive. Okay, so let's provide a graph of the uniform density function. So it's going to be very similar to what we see above. All right, so let me draw a vertical axis, a horizontal axis is our x value. And what do we have here? Well, we know that it exists for times between now and 50 minutes from now. So now is going to represent 0, and 50 minutes from now, well, that's 50. Okay, and we know that it's a uniform probability of arriving anytime between now and 50. Okay. Now, for this to be a uniform distribution, the area underneath this curve has to be 1. So really, by design, we have to figure out what value we have to put for the height here. Okay. So we know the area must be equal to base times height. All right. Now the base here, well, that length is just 50 minus 0, right? 50 minus 0, which is just 50, right? That's that length. Right? That's like your A and your B. And the height here, well, for this to be, if the base is 50, for the height, 50 times what will give you 1? Well, you need those 50s to cancel out, so you have to have a 50 down here. So it has to be 1 over 50. Okay, so again, if we're using that template from above, your height here would have to be 1 over 50 minus 0, right? That's like your A, that's like your B and your A, which would be 1 over 50. Okay. All right, so now that we have established the probability distribution and the area underneath that curve is equal to 1, now we can ask all sorts of probability questions. For example, what is the probability that you will have to wait between 15 to 35 minutes for the train to arrive? Okay, so again, let's go ahead and draw this exact same picture. I don't want to write everything on the above because it'll get too cluttered here. We're going from 0 to 50. We know that the height here is 1 out of 50. These are your x values. Okay. And, well, 15 and 35, well, if I'm eyeballing it at all, I would say at the center we have 25. 15 would probably be around here. Let me use a different color for that. 15 should be like around here. I would say 35 is around here. Okay. Now, if we're looking for probability, well, that's the probability that's between 15 and 35. Well, that's just the area of this rectangle here. Okay, so in symbol format, what it's really asking here is probability that x is between 15 and 35. Now, it doesn't matter if you have the equal sign or not. And if you've been paying close attention, you should know why. And that is because the probability of any single value is 0. So if you include 15 as an endpoint, it doesn't add to this probability at all. Okay. Okay, so this area is what? Well, what's the base here in this case? What's this distance here? Well, at least, so here with the base times the height. In this case, the base. Well, what's 35 minus 15? Isn't that the base? What does that give us? 20. What would be the height here? Well, it's 1 over 50. Let's go ahead and multiply those out. We get 20 over 50, which is reduces down to 2 over 5. Or this does terminate as a decimal. That's 0.4. And 0.4 is, well, it's 40%, right? Does that look like 40%? I know it wasn't super precise with my drawing, but that seems about right. Okay. Okay, so next question. What's the probability that you have to wait exactly 25 minutes? Okay, again, if you've been paying close attention, especially on the first page, then you should know what this probability is. Let me go ahead and draw the picture again to reproduce this. Okay, what's the probability that we have exactly 25? So they're asking, what's the probability that x is exactly 25? Well, if you look at the page above, the probability of any particular value on a continuous random variable is 0, because this is just one value out of an infinitely many amount of values, right? This continuous random variable is from 0 to 50. There's an infinite amount of possibilities, an infinite amount of times between 0 and 50. Okay. As a picture, if you're looking at the picture, here's 25, right? What's the area underneath there? Well, there's no width to it. There's a height there, which is 1 over 50, but there's no width to that. So again, if you're talking about area, there's no area there. So again, the probability is 0. Let's do another example. The reaction time x in minutes of a certain chemical process follows a uniform probability distribution. So they're telling us that it's uniform. And that time ranges between 4 and 9. Okay. Draw the graph of the density curve. Okay, so again, they told us it's a uniform density curve. So now it only exists between 4 and 9. So if this is 0, if I say that's 4, I would say maybe like over here is 9. Okay, you know it's uniform, so it only exists between 4 and 9. So this chemical reaction can only happen between 4 minutes and 9 minutes, and there's an equal chance of it happening within that time. Okay. All right, so what do we need here? Again, we need the height here to essentially force this to be an area of 1. Okay, so this again is by design. All right, so this is like your A, and this is like your B, 9. So again, we're going to do 1 over B minus A, which in our case is 1 over 9 minus 4. 9 minus 4 is 5. Okay, and again, just to reiterate that, it's the base times the height. The base in this case, 9 minus 4. The height here would be 1 over 5. 9 minus 4 is 5 times 1/5 equals 1. Okay, so we drew the graph. Now we can start answering questions in reference to probabilities of this random variable. It says, what is the probability that the reaction time is between 5 and 7 minutes? Okay, let's go ahead and draw that picture again. Here's 4, here's 9. That's our uniform probability distribution. The height here is 1 out of 5. Okay, so if we're looking for the probability, that means area, right, underneath the curve, that the reaction time is between 5 and 7. All right, so you know what? I'm going to break this up into what? 5, 6, 7, 8. Yeah, here we go. 5, 6, 7, 8. 5, 6, 7, 8. All right, we're looking for reaction times between 5 and 7. Okay, we're looking for that area. So again, that is in symbol format. That's probability that this x variable is between 5 and 7 minutes. And that is equal to, well, what's your base here? And what's your height? Let's switch up the colors here. The base is, well, it's 7 minus 5, right? And the height, we've already established that that's 1 out of 5. 7 minus 5 is 2 times 1/5 is equal to 2 over 5 or 0.4. Now if I look at this picture, it does look like it's 0.4. Here's another one. What's the probability that the reaction time is less than 7 minutes? All right, so let me go ahead and reproduce this graph again. We have 4, here we have 9. Here's 1 out of 5. These are our x values. All right, less than 7 minutes. So again, if I would do like 5, 6, 7, 8, 5, 6, 7, 8. Here's 7, less than, so that's to the left, right? Now, it doesn't go all the way to, I guess, negative infinity. It just goes to where this function exists. So it goes from 4 to 7. Okay, again, they're looking for probability, so we're referring to the area of this region. So the probability that x is less than 7 is equal to, well, it only exists from 4 to 7, so that width there is, well, 7 minus 4, right? And again, the height is still 1/5. 7 minus 4 is 3 times 1/5 equals 3/5 or 0.6. So now that we've established how to deal with probabilities for continuous random variables, namely for the uniform distribution, now we're going to go on to the normal curve. Okay. Now the first thing you notice is that this curve is a weird shape. It's not a rectangle like the uniform distribution, right? So we have to come up with a way to figure out what the area is underneath this curve. Okay. Now, if we find something that is a normal distribution, we say that x is distributed. This little tilde sign means distributed, normal, where we have a mean mu and a standard deviation sigma. Okay. We can have two normal distributions that have the exact same standard deviation, right? Meaning they have the same spread. But if they have different means, like 0 and 3, then they're just going to be out of sync in this case, out of phase. Okay, one's just shifted over by 3 units. But they essentially look the same. Okay, and that's because of the standard deviation. Now, this next one, both of these have the same center, the same mean of 0, right? However, the tall one here, I wouldn't really focus on the height here, but more on the width, the spread. The spread of this pink one is 1, so it's, if you're looking at the spread out, that it's less spread out than the other one, the blue one, which is a standard deviation of 2. That one's more spread out. Okay. Now, why does that height go up there? Well, because if you make it skinnier, then you have to make it tall so that you can conserve that area of the curve being 1 underneath that curve. So some of the properties of a normal density, the curve is symmetric about its mean. Okay, that just means that the left-hand side of this curve is a mirror image of the right-hand side. The mean and the median are the highest points. So in this case, the mean and the median are the same center here. Okay, we have inflection points. Now this is really only useful for when you're drawing this graph. It's not really super important, but when you're drawing this graph, what we call inflection points is where it changes curvature or concavity. And those are these 2 points right here, where it kind of the curvature starts to change. And that occurs at plus or minus the standard deviation. Again, the total area underneath this curve is equal to 1. The area to the curve to the left of mu is equal to the area to the under the curve to the right of mu, which is equal to 0.5 on both sides. So it's the mean splits this area into 50% and 50%. All right. Now we also know that the tails here, it doesn't go straight to 0. It actually asymptotically gets closer and closer to 0, but doesn't really hit 0. Okay. All right, now we did talk about bell-shaped curves before, and that had to do with this 68, 95, and 99.7 rule. So that all still applies. In fact, I do still owe you an explanation of where this 68, 95, and 99.7 rule comes from. Okay, and we'll talk about that in this section. All right, so I haven't taught you how to come up with these areas yet. Okay, so but once we do get these areas underneath the curve, they're going to represent either probabilities or percentages. Okay, so suppose a random variable x is normally distributed with the mean mu and a standard deviation sigma. The area underneath the normal curve in any interval of values of the random variable x represents either the percentage of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have some sort of characteristic described by the interval of values. Okay, it's best illustrated with an example. All right. So assume that the distribution of giraffe weights is normal. Okay, again, anytime you see that word normal, it just means bell shape. And we know that the mean weights are 2,200 pounds, and the standard deviation is 200 pounds. So the average spread is 200 pounds from that mean. It says draw a normal curve with parameters labeled and shade the regions under the normal curve for the giraffe that weighs less than 2,100 pounds. Okay, for all these problems when you're dealing with normal distributions, you want to make it a habit to draw a normal curve. So you're gonna actually do this quite often. Okay. Okay, that's close enough. All right, we always want to label the center, which in this case is the mean. And then in this case, it's 2,200 pounds. Now we can add on the standard deviation and then subtract off the standard deviation, and that should be around the inflection points. Again, this is just to kind of draw it pretty precisely. The standard deviation is 200 pounds, so if you subtract down 200 pounds, you're down at 2,000. And if you add on 200 pounds to the mean, you're at 2,400. Okay. They specifically were interested in finding the weights of giraffes that are less than 2,100 pounds. All right, so where's 2,100 pounds? Well, if that's 2,000, that's 2,200. I would say here is 2,100 pounds. Okay, so I'm going to draw a vertical bar there. And they're interested in the region and shading the region of giraffes that weigh less than 2,100 pounds. Right? Less means, well, to the left. Okay, so it's all this. So this is the proportion of giraffes that weigh less than 2,100 pounds. The mean splits the area into two equal parts, right? 50% and 50%. This shaded region seems to be less than 50%, right? Less than half of this. So I already know that this probability is going to be less than 50%. Okay, so that's a little bit of intuition. Okay, now again, I haven't shown you how to come up with that value. I do owe you that explanation. But let's just say that we are given that value, which we are in the next part. If the area underneath the normal curve to the left of 2,100 is 0.3085, so they're saying that that's about 30%. What are two interpretations in the context of the problem? Okay, again, we did say that the interpretations of these types of shaded areas can either be a percentage or a probability. Okay, so the first interpretation could be that the percentage of giraffes whose weight is less than 2,100 pounds is, well, 0.3085 is, well, in percent form is 30.85%. The other interpretation is that the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. Okay, so that leads us to something we haven't answered yet, really. How did we actually get this number? Okay, well, how do we calculate those areas underneath the normal curve? Well, we have two options that are typically done when learning this stuff. The old school way was they have tables of shaded regions, so you can look up these shaded regions on a table, or we use technology, so something like a calculator or a computer program. You can actually look these up online. There's a lot of websites where you can just type in values and you can calculate areas and all that. Okay. Now in this class we're going to use a calculator. Okay, I'm going to use a TI calculator. All right, so how is that done? Okay, and I want to relate this back to the uniform density function. Okay, so how do you actually calculate areas with the calculator? Well, I'll tell you what the calculator is doing on the back end. Okay. Now this function has a weird equation associated with it. You're not responsible to know this equation. That's why I didn't write it in the notes. But the function value here is 1 over the square root 2 pi sigma squared times e to the negative x minus mu over sigma quantity squared. Okay, so that looks kind of complicated, and it kind of is. Okay, now what your calculator actually does, it breaks up this. If I was, for example, trying to look for the area between -2 and let's say 1, I would actually break this up into little tiny intervals and create little rectangles. Okay. And so forth. You can just kind of do that. And the smaller the width of the rectangles are, the more accurate this picture gets. Right, because you can see how there's a little bit of gap in between the curve and the rectangles. And if you were to add them all up, that'll give you the total area. Okay. Now, if you're a calculus student, you might say, oh, I can just take the integral of this and get the area of this. Well, it turns out this is not integratable. Okay, so you'll have to do this numerically, which is what the calculator does. It does this numerically. Okay. But again, that's beyond the scope of this course. What we're going to do is we're going to be able to specify a lower bound, an upper bound, by the mean, the standard deviation, and our calculator is going to do the rest and calculate the areas for us, which is nice. Now this next part is somewhat of a history lesson, because in this case we're not going to be using the tables, but what was done in the past, it's still done today in many classes, is that if we have a random variable x, we have to convert it over to a z-score, okay? Because the tables in the back of the textbook all had areas for z-scores, okay? So if you can convert all your variables into a z-score, then you can actually look up these areas, okay? So we're not going to have to worry about that in this class. But I just wanted to be complete and show you that. All right, to find the area underneath the standard normal curve using a calculator, we're going to use a function. It's in the same area where the binomial CDF and binomial PDF are, second vars distribution. And we're going to look for something that's called normal CDF. Okay, we're also going to see something that's called normal PDF. We're never going to use that. We will never use this. In our class. Why is it in our calculator? Well, because it's used to draw graphs. Okay, so we will never use the normal PDF. We're always going to use normal CDF. Okay, what are the inputs? Well, we have the lower bound, your upper limit, your mean, and your standard deviation. What they mean by lower is really, what they mean by that is leftmost value. Upper is rightmost value. Okay. For a standard normal, the mean is going to be 0 and the standard deviation is 1. Okay. Now, if our upper and lower limits go all the way to infinity, we're going to use the largest number our calculator can handle. Okay, and that's E99, whether a plus or a minus. Okay, and I'll show you how to access that E. This represents 10 to the 99th power. All right, so we're going to do a bunch of examples in rapid succession, and that way you're going to get accustomed to using your calculator. All right, so for this first example, we are going to calculate the area to the left of the specified z-scores. Okay, and these are all standard normal. Anytime you hear this word standard normal, that means the mean is 0 and the standard deviation is 1. Okay, and that's going to be what we're dealing with in this entire page. All right, so for part A, it says we want to find the area to the left of negative 1.38. Well, here's 0, negative 1, negative 2. So negative 1.38 should be somewhere around here, negative 1.38. Okay, and we're shading to the left because that's what they told us to do. And we want to find that area. Well, we can use a little bit of intuition to kind of see at least what it should be in terms of whether it's more than 50% or less than 50%. Well, I can clearly tell that this is less than 50% of the shaded region. So our probability should be less than 50%. All right, so how do you find this area in our calculator? All right. Well, we're going to use something called a normal CDF. Okay. We have 4 inputs: lower, upper, mean, standard deviation. Okay, a lower value is the leftmost value. So if you go all the way to the left of the shaded region, well, that's all the way to negative infinity, right? Our calculator doesn't have a negative infinity symbol. So the proxy for that is to put in negative E99. Okay, and make sure you're using the negative symbol, not the subtraction symbol. Okay, that's one of the most common mistakes. Okay, the upper bound, or the rightmost bound, is, well, that negative 1.3938. The mean, since we're dealing with the standard normal, it's 0. Standard deviation is 1. All right, let's switch over to the calculator. Really. All right, from a fresh home screen, you want to make sure that that's all cleared out. Let's go to second distribution. Again, we see a normal PDF and a normal CDF. We will never use a normal PDF in this class. We're always going to use normal CDF. That C represents, again, cumulative. So it's going to accumulate from some lower value up to some upper value. Okay. Again, if your calculator doesn't look like this, then put it into your calculator just the way you see it on page here, where you have negative E99, comma, negative 1.38, comma, 0, comma, 1. Okay. But if yours does show you this user interface right here, then just go ahead and put in everything in correctly. All right, so we want to start off with negative E99. All right, so the negative symbol is not the subtraction symbol, okay? It's right underneath the 3, this little minus with the parentheses there. That's a negative symbol, okay? Okay, the E that we're looking for, okay, you see where the 7 button is at? Right above you see a comma, and then in blue it says EE. Okay, that's what we're looking for. Even though it says EE there, when you do second and that comma button, it's just going to be an E, just a single E. You just need one. And then we put in 99. Okay, that's essentially negative 10 to the 99th power. So that's the largest negative number that we can find. Upper would be, well, in our case, it's negative, same symbol, negative 1.38. Then we have 0. If it's not there, just put in a 0, and then 1 for the standard deviation. Let's go ahead and paste that over to our home screen. Again, if you didn't already know if your home screen was cleared out, if you just press second and then to the left, you'll be able to see if there was anything in front of that. Because if there's anything in front, it might multiply it out, and you'll have a wrong answer. Okay, again, you can navigate back and forth. Second right, second left, second right. Okay, let's press enter, and we get about 8%. And just by looking at the picture, it does make sense that well, we knew it was going to be less than 50%. In this case, 8%. Okay, doing the next one. 0.87. 0.87 is between 0 and 1. So I would say it's like around here. Draw a vertical line straight up. And they're asking for area to the left, so we're going to shade to the left here. And just by using a little intuition here, does that appear to be more than 50% or less? Well, it looks to me like it's more. So I expect it to be more than 50%. Again, this area is going to be normal, CDF. We have a lower, upper, mean, standard deviation. The lower, again, it's all the way to negative infinity. Negative E99. Upper, 0.87. Mean, 0. Standard deviation, 1. Okay. If you do that and put that in your calculator just the same way that we did the previous problem, you're going to get 0.8078. So that's about 80%. So it does seem like it. Well, it is more than 50%. Okay. All right, let's do another one. Now we're going to shade the area to the right of the specified number. So negative 0.21, here's negative 1, here's 0. I would say negative 0.21 is right there. So, and then we're asked to shade to the right of that. Do we expect it to be more than 50% or less? Well, to the right of 0 is 50%. If this is a little bit more, then I expect this to be more than 50%. Okay, so normal CDF, we got our lower, upper, mean, standard deviation. Our lower being what? In this case, it's negative, because it goes from left to right, negative 0.21, comma, upper, that's a positive infinity, so you just have to put the E 99. The mean and standard deviation is 0, 1, because we are dealing with a standard normal. Okay, if you run this through your calculator, just like we did before, this will be 0.5832. All right, let's do another one. 1.25, well, here's 0, here's 1, here's 2. I would say 1.25 is about there. Draw a vertical line. Again, we are being asked to shade the area to the right of this. Okay, that looks like a small area. It does look like it's less than 50%. So if we're finding the area here, areas are found underneath the normal distribution by using normal CDF. You have our lower, upper, mean, standard deviation. Lower being, in this case, 1.25, upper, positive infinity, E99. Mean is 0, standard deviation is 1. And again, if you run that through your calculator, you get something as expected, less than 50%, in this case 0.1056, about 10%. All right, so we did to the left, we did to the right. What's left? Well, what if we're looking between two values? Okay, between two specified values. So two numbers have to be specified in this case. So we have a lower bound, a leftmost bound, and a rightmost bound. Okay, negative 1.21. Well, here's negative 1, here's negative 2. I would say negative 1.21 is around here. 0.98, that's really close to 1. So I would say somewhere around here, right? 0.98. And we're looking for the area in between these two values. Okay, so we find that using the normal CDF. We have lower, upper, mean, standard deviation. Okay, our lower bound this time is, well, it's negative 1.21. Again, the leftmost value of the shaded region, negative 1.21. Upper, 0.98. You notice we didn't have to use E99 at all because we're not going to negative or positive infinity. The mean is 0, standard deviation is 1. Again, if you run that through your calculator, in this case, it's kind of hard to tell. Use some intuition to see if it's more than 50% or not. But this turns out to be 0.7233. Okay, let's do another one. 0.33. That was, it's positive, so it's somewhere around here. 0.33. Let's say it's somewhere around there. 2.25. Where's 2? Here's 2.25. I would say, roughly. And we're looking for that shaded region. This one I can actually use a little intuition, because beyond to the right of 0, it's 50%, and this looks like it's definitely less than that area, so it should be less than 50% here. Again, we're going to be using normal CDF. We have a lower bound, we have our upper, we have the mean, standard deviation. Our lower here is 0.33, Upper is 2.25. The mean and standard deviation are 0, 1. Again, that's because we're dealing with a standard normal. Again, if you run this through the calculator, we get something like 0.3585. Okay. Okay, so one last example. And I did promise you something earlier, right, about that empirical rule. What the empirical rule says is that 68% of your data lies within 1 standard deviation from the mean. 95% of your data lies within 2 standard deviations of your mean, and 99.7% of your data lies within 3 standard deviations from your mean. Okay, so let's see if that's true. Let's find the area between, in this case, -1 and 1. Here's -1 and 1. Okay, let's use normal CDF. We have our lower, upper, mean, standard deviation. All right, what's our lower bound? Well, it's -1. Upper bound, 1. Mean, 0. Standard deviation, 1. Why? Because it's standard normal. If you run that through your calculator, we get 0.6827. Again, there's our 68. Same thing here. Normal CDF, lower, upper, mean, standard deviation, -2, 2, 0, 1. And what do we get here? 0.9545. Okay, so when rounded to 2 decimal places, that's 0.95. And then finally, within 3 standard deviations, it looks like it's almost all the shaded region. There's just a little bit of empty space in those tails there. And the area here would be normal CDF, lower, upper, mean, standard deviation. Again, -3 up to 3. Mean is 0. Standard deviation is 1. And if we run this through your calculator, we get 0.9973. Okay. This is that 99.7 rule, right? When rounded.